Our next speaker is Christopher M. Tessum. He is an assistant professor of civil and environmental engineering at the University of Illinois at Urbana-Champaign. His research assesses air pollution-related effects of human activity, focusing on mechanistic modeling of outdoor air pollution and its health impacts, quantifying inequalities in the distribution of those impacts, and proposing and testing solutions. He studies the relationships between emissions, human activities that cause them, and the resulting health impacts, and develops modeling capabilities to enable these types of analysis.
All right, thanks everyone. So for having me. So I'm going to be talking about equation-based geoscientific modeling and surrogate modeling. So first, some terminology. I think probably everybody already knows this, but yeah. Oh. Maybe if you go like this. And then. All right. So probably everybody knows this, but just geoscientific modeling, kind of numeric models of the Earth system and its components. I want to make a couple of points here. One is that, it's a pretty big area of science, right? I think we all know this because we're all here. But I want to put this here also because I'm going to transition really quickly here into talking about my specific area of expertise, which is air pollution. But I want to kind of keep in mind that the techniques that we're going to be talking about are pretty general and can be used in other areas of geoscience. All right, and so now I'm going to transition to air quality. And so I want to try to convince you that air pollution is important. So there's a couple of facts. One is that air pollution kills a lot of people. So it's about 5 million people per year globally, about 100,000 people per year in the United States. It's usually the largest environmental risk factor for dying. So that's one thing to keep in mind. One reason why we'd want to model it, study it. Another is that a lot of us are kind of working somewhere kind of related to climate science. And so if we're talking about climate mitigation, climate action, a lot of that is, at least in the United States, kind of comes down to air quality modeling in a kind of a weird way. And so I'll illustrate that here. So here, this is a process that's actually currently going on right now. So we have this Dominion Energy company who they're trying to they have power plants. They're trying to demolish one of them and build a newer, bigger one, I think presumably to power data centers in Virginia. And so when a power plant company wants to do something like this, they need to get an air quality permit that says that they're not going to break any, result in any laws about air pollution being broken when they build this new plant. And so they submit their application, and then there's this public review period where, in this case, they got around 4,000 public comments, and then the Department of Environmental Quality has to write this, response to it. And so here it's like a 40-page document. In this 40 pages, they have, they mention the word model 150 times, right? So it's all modeling. It's, and so this process about whether the power company can build a power plant or not comes down to this kind of model battle, right? So hopefully I've convinced you that air quality modeling is important. It's important to say kind of what's our environmental future. And the reason for that is that the air pollution laws, at least in the United States, are the ones that have teeth, right? The climate laws don't. So if this air quality modeling is important, we probably want to know what is an air quality model, right? And so when I think about it as like an academic that works in this area, what an air quality model is, I usually think about something like this. So on the right side, we start with estimates of what the emissions of air pollution, different air pollutants are, and shown there. Then on the right side, so left side first, right side second, we have to bring in information about meteorology, so wind speeds, directions, mixing, radiation, things like that. And in the middle, then kind of the main thing that we do is we have this big model that shows how after the pollution is emitted, how it's kind of transported around from location to location, how it's transformed to become more or less toxic with chemical reactions, how it's removed from the atmosphere but through different processes, and ultimately how people are exposed to it. Right? So these are complicated models. They're difficult to run for a number of reasons. There's a lot of processes that need to be represented. They're computationally intensive. There's a couple other reasons that I'll get to in a second, right? But this is kind of, the work that I do, something like this, right? How if we ever go back to the model battle that I just showed you in that document, what I just showed you there, that's not what they're doing, right? So in the model battle, they're doing something like this, where they have, you have a smokestack. The emissions come out of this smokestack. They go up a little ways, and then they just go in a straight line, right? And so when we have all this effort going into, should we be allowed to build this power plant or not, it's kind of operating at this level of science, right? At the best, and that's the power plant will usually run a model the power company will use a model like this to try to show the impacts, and then the other groups that often don't want the power plant to be built in their neighborhood will either say, well, you did this modeling wrong in some way, or they try to do their own modeling, which would be similar. But a lot of times, these kind of processes are not informed with the best science, right? And so I have I think there's a number of reasons why this is, right? I'm not going to be able to fix all of them, obviously, but I have a hypothesis about one reason why, right? And so for the people that are engaging with this are usually going to be environmental scientists, atmospheric scientists, geoscientists, things like that. They're usually not going to be computer scientists, right? And so geoscientists, physical scientists tend to think about the world in terms of equations, in terms of reaction systems, things like that, right? What they don't tend to think of is something like this. So this is a seashell script, script, which is just kind of one of the things that you might use. I don't know what's going on here. Maybe try the different. One of the things that you might use to, let me see. There's a label on this that says not working properly. That's it's not a good sign.
It's supposed to be that one is working.
Okay. It's just
It's all right.
we're back. Okay. I just need to not touch it. All right, so this is some sort of computer code, and so when you get people who are trained in environmental science, usually they're not they're just not able to natively interact at this level, right? I didn't touch it that time. Okay, now it's back. Okay, maybe this will work better. All right, so in general, physical scientists a little bit more comfortable with something like this than something like this, right? And so the issue is that all these models, even the simple ones, are usually, they're implemented in some way where you have to do a lot of this kind of computer code in order to use it at all. And just a lot of physical scientists aren't able to do that. So if that's one reason what's kind of, keeping good science from really being used in these processes, then a way that we could kind of get around this, we could fix it, is by thinking differently about how we develop our models, right? So instead of typically now they'd be written in Fortran or something like that, instead we can try to write them, in terms of equations. So when you're, if a scientist that's developing a model, they'd write down, reaction systems, for example, that would go into the model, right? They write down systems of equations that would go into other components maybe. And then information about how the different components would be coupled together by setting different variables in different component systems equal to each other, right? And so that's what a human would do in this case. And then kind of the rest of everything that would go into model development would be happening automatically, right? So you take all your different systems of equations, couple them together, kind of simplify them into one big system of equation, generate code from that, and then do various different steps to kind of make that code more efficient and something that can run on actual hardware, right? And so that's kind of what we're working on, what I'm kind of going to show you about here. So obviously, this is not something I could do by myself. It's built, so our code that we write is called, we call it EarthSciML. That's the one in orange there. But then it's kind of built on top of and within this entire ecosystem. It's, I think, developed by some people actually in this room that know it better than I do. Feel free to tell me if I've got my arrows in between the different components all mixed up. But we think at this point we can kind of do this. So this is one example of what we can do. So here's it's a model result of predicting ozone, which is one of the chemicals that we care about. It doesn't matter too much except the fact that it does actually work. So on the right side over there, we see basically time and the concentration predictions, the average. So the blue line is the observed, so like actual measurements of ozone at the ground level, and then the red and yellow lines or red and orange lines are model predictions. So our model is kind of under predicting at this point, but it's we're working on it. I think at this point it's something that could actually be used in certain applications that are not too dependent on accuracy. And so that's one thing we can do. We think it might be useful if it's fast enough. So we've also started to figure out how fast it's able to run. So on the left here we have what is a work precision diagram, and maybe some of you are already familiar with this. If you are, you probably will think that the axes are backwards. So usually the x and y axis would be split or be switched. But we can see here one thing that we can do that you usually can't do with normal air quality models is that we can use different methods to solve the equations. So the ones in the dotted lines up here are ones that we've kind of hacked together, kind of a normal way to solve systems of equations for an air quality model using string splitting. And then the ones with the solid lines are some of the ones from the differential equations packages using implicit explicit methods. And so currently, the implicit explicit methods are more accurate, but they're slower than our kind of handwritten ones. I think this is going to be a pretty typical case in geoscience modeling where there's, these models are very kind of hand-tuned and hand optimized to work well with certain situations. But I think, with work that we can get these kind of standard methods to work, be both faster and more accurate at time. And then over here, we on the right side, we have information about how the runtime scales with the number of grid cells in our model, right? Ideally, we want to run the model with a lot of grid cells at high resolution. And then, so those are the lines on the top are our model. And then the ones at the bottom are a different model that I made in graduate school that does kind of a similar thing. And so you can see our new model with these equations is a little bit slower now, but it tends to scale a little bit better with the number of grid cells. And again, we think that we can probably speed this up. And we'd be obviously very interested in working and discussing with people on ways to do that. So just as a kind of example of once we have the system working, what we can do with it. So here, this is, a lot of times something that you want to do, something that, we showed at the very beginning. You want to make some sort of simulation about what the existing kind of business as usual type of environmental situation is, air pollution in this case. And then say, how would that change if we were to change some sort of input? All right, so here we have some code to, import our packages, set up a space and time domain that we want to run the model on. Kind of put together the baseline configuration components of the model that we want to run. So we have, chemistry, photolysis, like radiation, things like that, deposition. And then we add in emissions for, from kind of all the emissions of air pollutants and in the United States in this case. And then we also have another scenario where we also add in a 30% reduction in emissions from cars and trucks on the road. And so we can do that with, this amount of code. Then this code over here runs the model, get these results here. For you, it doesn't really matter what these results are. But kind of the key takeaway is that, we can do this in something like 30 lines of code, right? And so, for me, like as a graduate student, this is kind of what I did in graduate school, but with the more kind of Fortran-based models. And to do something like this, just to kind of configure the model and maybe not even run it, with a more traditional model would take like several weeks or a month for me, like now as a professor, right? So is to the extent we can get this all working, it really does streamline the process of this type of analysis. Another thing that we can do is, so there are different kind of frames of reference that can be useful in this type of modeling. So the one we have back here is where we had kind of split our domain into grid cells and track how things move in between the grid cells. Call that an Eulerian frame of reference. Another thing that sometimes we want to do is say our frame of reference is a packet of air or fluid and track that packet as it moves around through the atmosphere. And so that's called a Lagrangian frame of reference. In both cases, it's the same system of equations, but just it's in a different form. Right, and so normally, if you have your kind of Eulerian model, your Lagrangian model, there's going to be completely two separate code bases with completely separate teams working on them that don't talk to each other at all. In this case, we can just use the same model, but make kind of a slight tweak to the equations, the way they're put together, and then we get the different frame of reference. And so we can compare that to a kind of traditional model that does the same thing. We can see that we get a similar result. We believe that we should be able to get our model to run faster than the traditional one, but we're not, not quite there yet. So far I've been, so far I've been talking about what I think is kind of the main bottleneck to be able to kind of democratize, kind of streamline this environmental modeling. Something that's going to be is important now. It's going to be more and more important as climate change progresses. And so, in my mind, kind of the main bottleneck is just the usability of these models, right? There's another one that I think is less of a bottleneck, but is still there, which is that they're very computationally intensive, right? So what if we also want the models to run faster, so we can use them for more things, more people can use them? And so there are a number of different ways to do this. One way is just to be able to solve the systems of equations faster using kind of different, mathematical techniques. I know some of you in the room are doing great work over that, and we're very excited about it. But also in kind of parallel, one thing we've been kind of working on different machine learning techniques to do this too. So kind of our approach to this here, there's a lot of different things that you could do. But what we're working on is to try to say we have this model that has a bunch of different components in it. And we're trying to take the individual components and kind of streamline each of them to be able to run in some way faster that gives similar results. So in an air quality model, the most computationally intensive part of it by far is the part that does the atmospheric chemistry. And so what we've been working on here is we can take a kind of a complicated atmospheric chemistry model. So here we have basically we have this kind of cloud, and the dots in the cloud are the different chemical species. There are 5,000 of them. And then there's these lines that represent the reactions in between the species, which are, in this case, 15,000. And by using kind of machine learning techniques, we can represent the same system with a reaction system that instead has 6 species and 12 reactions, right? So it's much, much faster. In some cases, our machine learning model and the reference model map to each other very well. In other cases, not so well. And so we're still working on that. But one thing that we're really excited about with this is that with this system, we give a mathematical guarantee that our simulation will always run, right? It's not going to go to infinity or anything like this. And this kind of issue of runaway error propagation has been something that's really been plaguing the kind of the field of atmospheric chemistry and machine learning for a while. So we're pretty excited. We think that we've kind of solved this, at least that part of it. And so you can see here, this, as you would hope, we can get several orders of magnitude of speed up. You can see in the red line, so this is a reference model. Here we have the machine learning models and on a GPU and a CPU. You can also see that one thing here we're still working on is this is the number of latent chemical species that we use to represent our system. ideally, you would hope that as you increase this number of species that you're kind of representing the system with, the more chemicals you have, the more accurate it's going to be, hopefully. So we are able to do that up to a point, up to 6 species, but then after that, it actually gets worse. And so we're still, we're working on that. And then over here, we can see basically, once we get to a certain point, if we're doing a bunch of simulations in parallel, like we would if we have like a big model with a lot of grid cells, at a certain point, we can get good speedups from using a GPU too. So one more thing, we're also working on doing machine learning for advection. So if the atmospheric chemistry is the most computationally intensive operator in the model, advection is the second one. So advection is where you have wind that's kind of blowing the pollution from one grid cell to another grid cell. So we're working on representing that using a convolutional neural network where we just have our concentration and the wind speed as the inputs, and then the flux from one grid cell to another grid cell as the output. A benefit of doing it this way is that we are able to get good properties with regard to mass conservation, which is important. And so here, I won't talk about it too much, but on the top here, we have this example simulation with our reference model where we have an initial condition here and then kind of how it evolves over time. And then down here, we have different machine learning models. And you can see that all of them, pretty much give the same, at least to the eye, the same spatial, pattern as our reference model. So it's working well. At this point, it's actually turned out to be much more difficult than I would have thought going in. But we think we kind of have it working now. And so you can see, so this on the x-axis is like how much of a speed up we get against the baseline, and this is the accuracy up here. And so you can see this red line to start with is our reference model, right? And so what we do in order to get a speed up is that we take longer time steps when we're solving the simulation, right? And so here with our kind of traditional model, we can double the time step and actually get the same result. We can also multiply the time step by 4 and get the same result. This suggests that we just had a relatively small time step to start with. But then if we try to multiply the time step by 6, basically accuracy goes to 0 and the model doesn't really run at all. And so this is kind of a traditional what will happen when you do fluid dynamics simulations, right? If you have a time step that's too long, it just doesn't work. And so what we're able to do with the machine learning model, which is in the blue and the purple dots here, is that when we can increase the time step by a certain amount and we get, it's still pretty good accuracy. And then we can do like 8 times or 12 times or 16 times or 32 times longer time steps and still have, kind of gradually degrading accuracy, right? So we can kind of get into this Pareto frontier type of situation where we can, in certain applications, maybe you don't need quite as much accuracy, and then we could get a good trade-off with speed up. And so one kind of very implementation detail that has turned out to be important here is this purple series of dots here is when we use the kind of traditional or the most commonly used machine deep learning framework in Julia called Flux.jl. And so when we do that, actually, a lot of the time, our machine learning model is slower than the reference model. So it's also, it's slower and also less accurate. So that's just like not something that we could say is useful. But when we take the same neural network and re-implement it in this other framework called Simple Chains, which is optimized for small neural networks, then we can actually get a system that's a lot faster than the reference model, right? So we go from, just by making this implementation change, we can go from the system that's not useful at all to one that potentially can be. So one final thing that I'll talk about because of where we are. So there's kind of, in geoscience modeling, there's a lot of applications for using optimization. So we use words like, data ingestion or data, no, I can't use the word, but data assimilation, that's it. Adjoint modeling, kind of source tracking, things like that, sensitivity analysis. I guess I tried to open a web page, but it didn't let me. Can I? Okay, there it is. And so, and this is kind of something that is, people really like to do it in geoscience, but there's often not very elegant ways to do it because it's all written Fortran. So we've been working on trying to get kind of auto differentiation to go through our kind of forward model simulation. And so we don't really have good results yet, but we have this demonstration that shows that it is possible. So I'm not really going to go through this, but we can go through and kind of auto-differentiate and get gradients, for some sort of inputs toward an objective for like our entire model forward simulation, right? And so this is important because, let me get this open again. Because we'd really like to optimize our model to kind of improve it, tune it against Earth observation data, or satellite data in particular. Right, and so that's something that we're really interested in going forward with and be very interested in collaborating with other people here that might be doing similar types of things. So in conclusion, hopefully I've kind of shown you that this idea of taking equations, implementing our model as equations, compiling them to a model that runs, can kind of really streamline this process of environmental analysis that becomes kind of increasingly important as climate change accelerates. And that through kind of surrogate modeling, we think that we can maybe make these models faster too. I've just kind of focused on air quality so far, but a lot of the techniques here are generalizable to other areas, and we are actively working, kind of bringing together groups to try to do this. So, thanks everyone. We, have the code is online, everything. Acknowledge the members of my group. Chris in particular, we've been collaborating with him and with the Julia lab. One thing also I just want to put up here, I know a lot of us are working in different ways with different satellite data. As far as I know, in Julia, there's like not a really currently kind of centralized, really great efficient package for pulling the satellite data off of the internet and doing all the things that you need to do to kind of get it into a raster that you can, raster an image or whatever that you can, they can directly analyze. And so that could be kind of an area of emphasis, community work. This is something that my group is going to be working on. So if there are other people interested too, we could kind of get together. There's an example of, in PyTorch, there's a package called TorchGeo, which could kind of be as a template. So thank you.
There we go. Thanks for a very nice presentation. I was going to ask you about adjoints, but you've already addressed that. So I'm going to ask you about, I guess, two things. One is, are you also looking at doing this in 3 dimensions? Or it seems to like maybe you're working mostly in 2D.
Oh, yeah, it's definitely a 3-dimensional model. It just, by convention, in my field, we only look at the ground level. But that's the 3rd dimension is there too. I just didn't show it.
Okay, I guess with the 3 dimensions and the adjoint piece, it starts to be quite competitive with something called Geoscam.
Yep.
Is that sort of where you think you are out already, that you could use this instead of Geoscam?
So the grant, a lot of this came together through a grant that we got from NASA that we were going to make a kind of an emulator of Geoscam. So that's kind of our template that we've been taking it from. It's not currently competitive from Geoscam because, where did it go? Because of this, right? The accuracy is not super great at the moment, but that's definitely our target.
Great, thank you.
Thanks for the great talk. I was just wondering, when you replace the advection by the neural network, do you do something special about conservation?
Like mass conservation? Yeah, so here, so we've done a bunch of different things. Some of them work better than others. But what we're currently doing, so basically we're predicting the flux from one grid cell to another grid cell. And so when you predict that, it is by nature mass conservative, right? We do run into issues where, there's nothing here that says that the model can't make predictions of concentrations that are negative. And when you make negative predictions of concentrations, it causes all kinds of problems. So what we do is any negative concentration, we clip to 0. Actually, our reference model also occasionally makes negative predictions, and we do the same thing, but this machine learning one does it much more frequently. And when you get negative predictions that you clip to zero, then you get mass. You're no longer conserving mass, but it's still it's works much better than it would if we didn't have that property.
Thank you.
Have you thought maybe at combining this neural network with some flux limiter to try to make some hybrid machine learning numerical discretization method to avoid this error of false extrema?
I've definitely told my student, the graduate student that's working on this, to do that, and I've given him a number of ideas. He's always come back and told me that that idea didn't work for different ways. So if you have ideas, we're definitely. I'm not like I'm not an expert in computational fluid mechanics. So I'm definitely open to ideas.
Thank you. I'm a conventional modeler.
Yeah.
So, if you said you told that you can conserve mass, and my question is, and what about concentration? Can you also produce realistic distributions of concentrations, or do we have overshoots of the concentration?
Yeah, so I guess I was using the words mass and concentration as more or less interchangeable. So I'm not completely sure if I'm going to be answering that question correctly, but basically we do a bunch of different tests that I've not really shown here. So there are a couple of issues that we do run into. One is that so you're probably familiar with a CFL number, right? So when we get if we're using CFL numbers that are outside of the range of the CFL numbers that we train on, then we get issues there. Another issue that we see is, especially when we have the longer time steps that we're training on, we get the power spectrum of the changes in concentrations is kind of, it's dissipative, I guess. So that's kind of an issue. We're still thinking about how to deal with that.
Thank you very much.
Thanks, Christopher. Could you go to your last slide?
The one about the
With
torch.
with the provocation about the torch geo.
Yeah.
Great talk. I like that point as well very much. So I suggest we discuss that later at 4, expert hour.
Yeah.